Remember to record. There we go.
So this, you don't have to do it again?
No, I put them on YouTube in case somebody missed it
Oh, okay.
or wants to go back and watch it. I'm not sure why. But. Okay, so we're going to talk about digital circuits, the binary numbering system, logic operators, logic gates. Maybe get Ernie to do that because he was just refreshing himself on how to do an exclusive OR. Some logic circuits, comparators, and analog to digital converters and digital to analog converters. So digital logic circuits operate in binary with two values, either 0, 1, high, low, off or on, true or false, 0 or 5 volts, just as long as there's two distinct states. And we can use those to represent decimal numbers where we go 0 through 9 and then powers of 10. In the case of the binary system, we're using powers of 2. So each state represents
Unique.
2. So we'll go up 2, 4, 8, 16, 32, on and on and on. And those are represented as 2 to the 0 power, which is equal to 1. Any number raised to the 0 power is going to be equal to 1. 2 to the first power is itself going to be equal to 2. 2 to the second power, or we call it 2 squared, is 4. 2 cubed is 8. 2 to the fourth is 16. On all up to infinity. Usually you don't see much beyond 32 bits. In some computers, 64 bits, but those are getting to be very, very large numbers. In a lot of cases, to make it easier, because binary is messy, particularly when you're just looking at ones and zeros, so we can use the octal representation or hexadecimal. In the case of octal, it's really base 8. So we take 3 binary bits at a time to represent the numbers. So it goes 0 through 7, and then we start at 1, 0 through 7 again, and on. In the case of hexadecimal, it's a base 16, so we go 0 through 15, but we represented it 0 through 9, A, B, C, D, E, and F. So we throw letters in there. But for large numbers, it's easier to deal with hexadecimal representations. This chart shows the comparison between the decimal numbers 0 through 10 and binary representation, what it looks like in octal, and what it looks like in hexadecimal. So a 10 in binary is going to be 1010. In octal, it's 12. In hexadecimal, it's 0A or alpha.
They don't always use that.
Huh?
They don't always use that numbering system when they're using the small change.
Oh, you're talking about gray code?
Yeah.
Yeah, we hadn't got to gray code.
Oh.
I don't know if it's on the tech.
Huh?
I don't know if it's on the tech exam.
I don't know.
What Ernie was talking about, there's a thing called gray code where they, let me back up, reorient the change in the numbers. So if you notice in binary, as we count up, we're all zeros, then the first or the least significant digit goes to 1. Then it goes to 0, and the next significant one goes to 1. And then we do a 1, 1, and then both of those go to 0 and 1. Well, we have multiple bit changes. Gray code reorients these patterns. So from one state to the next, there's only a single bit change, which helps in some communications and decoding.
Weak signals,
weak signals.
that's where it is.
We have basic logic operators of and, or, and not. In programming, you'll normally see it represented and as a double ampersand sign, or as two pipes, and the exclamation as a not. Just writing Boolean algebra. Let's see. For an and, this is kind of what we call a truth table. So if I have two trues, the output is going to be true. In other words, I had a 1 and a 1, the output's a 1. If I have a true and a false, the output will be false. If I have a false and a true, the output will be false. If I have a false and a false, the output will be false. So for an AND gate, the only time the output is true is when all of the inputs, it doesn't have to be just two, it can be 3 or 4, or however many. I think I've seen maybe up to 8 in a single package. The OR function says if I have a true or a true, the output is true. So as long as any of the inputs are true, the output will be true. And that's the case of true or false or true. At least one of them is true, so the output's true. So it only goes false or 0 when all of the inputs are false or 0. Not is just the inversion operator. So whatever the state is, the output is the opposite. So if I have I'm not sure why I'm showing that there. If I have a true coming into an inverter or a not expression, the output is false. If I have a false coming in, the output's going to be true. So these are the basic logic operators we use to build everything else. So we can buy logic circuits or integrated circuits that have these elements packaged in them. Like in the case of inverters, there's usually hex six inverters in a normal package, in a 16-pin package or 14-pin. Yes, they're 14s.
14.
Huh?
14 is 6. Right?
Yeah. Power, ground, and
right.
You can also have OR gates. You can have AND gates. You can have NOR gates, which is an OR gate with, you'll see it represented with a small circle on the output to indicate that that's an inverter. So it's whatever the output would normally be, this inverts it. And the same is true for the AND. And we would call that a NAND gate in that case, and this would be a NOR gate. Now, it turns out from an implementation standpoint, it's easier to build NORs and NANDs with the transistors than it is ANDs and ORs. It takes more transistors to make an AND gate than it does a NAND gate. Right, Ernie?
I don't know the insides.
Trust me on that one.
I trust you.
Okay. And again, we're showing the truth, what we call truth tables. So for the inverter gate, a 0 in gives you a 1 out, a 1 in gives you a 0 out. For the OR gate, before I messed it up with circles, if both inputs are 0, the output is 0. If either input is a 1, the output's going to be a 1. In the case of the AND gate, the only time, I'm covering up the bottom down here. That bar's always in the way. The only time the output is going to be true or 1 is with all of the inputs are 1. So an easy way to remember how gates work is just draw a little truth table. And if there are, two input, then you just need these four states, and it's fairly easy to remember the difference between an OR gate and an AND gate. Okay. This is just a simple circuit showing a clock signal, which is just a square wave. In this case, it's a 1 megahertz square wave. It doesn't really matter what the frequency is. So that's our input into this inverter. And the output is just the inversion of it. Any questions so far?
Nope.
Okay. This is showing the same thing with an AND gate and a NAND gate. Okay. So they both have the same inputs. In this case, it's two clock signals, one's at 4 hertz and one's at 2 hertz. So you can see the input of the 2 hertz up here and the 4 hertz there. So it's really twice the frequency. And the output of the AND gate is only going to be true when both of the inputs in stage 3 are true. The NAND gate is going to be true except when the inputs are true. So it just inverts whatever the AND is. Okay, so now that we've got gates, we can put them together and make things like flip-flops. Or maybe I'll get Ernie to draw his exclusive OR. So if we take these 4 NAND gates and an inverter and put them together like this, so there's basically feedback, it will create what we call a flip-flop, where it'll maintain a state until you change it, and then it retains that state until you change it again. So in the case of this configuration, which we call a D flip-flop, it's also called a register because we use it to store information. So when we get a clock signal on the rising edge, whatever the state of the D input is, or the data input, the output will go to that state. And the opposite output, they usually have 2. We call them Q and not Q. So one will give you the inverse of the other one. So that's very useful in combining a lot of these together to make counters and things like that. Now we have a different configuration where I'm not showing all the gates. It takes a lot more to make a JK flip-flop. And we call it a JK flip-flop because we labeled the inputs, instead of having just a D input, it has a J and a K input. And depending on the state of the J and the K determines how it operates, either as a register or a flip-flop. In this case, if both J and K are 1, every time there's a clock signal, the output is going to toggle or change state. So they're very useful to make counters. It's harder to make counters with D flip-flops. This is showing a 3-bit counter made from 3 JK flip-flops just interconnected. And we call this a ripple counter because when the first clock pulse comes in, the output of the first flip-flop changes, which is fed to the clock of the second one, which causes it to toggle, which goes to the third one, which causes it to toggle. So you see this ripple effect if you look at it on a timing diagram. Because in the real world, there's many nanoseconds delay between this one and this one and this one.
The change is when the clock output goes to 1. In this case.
Well,
When
actually
it goes
on the
back to
rising
0,
edge.
The next change. The first one, when the Q becomes 0, it doesn't trigger number 2 until it goes back to 1 again.
Right. Right.
That's how it gets to the
Right.
3.
Because each clock toggles it on a rising edge. So you have to have a positive going pulse in order to toggle each one of these. Which, if you look at the trace down here where I ran a simulation of this, let's see, the bottom is the actual output of the first stage, flip-flop 1, and then 2 and 3. So you can see it as it counts. We're toggling. So every other clock, we're getting a 1. And in this one, then we are toggling that again whenever there's no, that doesn't look right.
That's the way it works.
Yeah, but these are changing on negative going clocks.
No.
Yep. That's going negative, and output of that one's going positive. So it's a negative clock, which might be in the simulator. Normally, you'd have a circle there to indicate it was a negative clock, as I recall. It's been a long time since I played Gates.
Me too.
The only thing you need to know, you don't need all those details other than to recognize a 3-bit counter and how many states. So if we go back, a 3-bit counter will count 8 states before it starts over. So that's really and I forgot exactly how it's worded, but that's really all you need to know is that a 3-bit counter counts up to 8.
With feedback, you can change the number.
Yes.
Question on that.
And it's covered up. This should say shift
Robert,
rate.
hey, just a quick question, because I'm seeing it's not a coincidence, but I'm seeing similarities. So a 3-bit counter, you said it has 8 states. Is that because 2 cubed is 8?
Yes.
2 to the third power is 8. So okay.
Right.
Yeah.
So each one of those flip-flops is a power of 2,
Yes.
and you're multiplying it.
Yeah. So yeah, a 3-bit counter will give you 8.
So if it was a
A
4-bit
possibility
counter,
of possibility of
count?
8 different states.
If it was a 4-bit counter, what would it count
Maybe
to?
16.
Okay. Right. Actually, it counts 0 through 15, and on the 16th one, it goes to 0.
Yes.
Right.
Got it. Yeah. All right. Picking that up.
Okay. So if we take our D flip-flops and we chain them together, we can make what we call a shift register. And whatever is on which is, I should have flipped it around. I don't like them going in the wrong direction. But over on the right is the input. So if this happens to be a 1 on the input, when we get a clock signal, it's going to change the output of this first stage. And we're clocking them all at the same time. So this stage, depending on what the output of the previous stage was, will possibly change or stay the same. If it was a 0, it's going to stay the same. If it was a 1, it's going to change this to a 1. So in effect, what it does, if I had a 1 here, every clock is going to move that 1 to the next stage and shift it from beginning to end. Oh, wait a minute. I'm looking at it backwards. That's not the input. I need my coffee. Or
maybe you just need better coffee.
well, I hadn't had any. So we are we're assuming this is at 0, all states. So if that's true, we're going to put a 1 on the D input. So the first clock that comes in is going to shift that to the output. And
The Q changes.
Q changes, but it's still going to be a 1 on the input. It's going to stay 1.
Any one will give you a 0 at the D.
Yes, you're right. So that will, right. So we're just going to shift a single pulse through, which is probably on the next slide.
Okay,
Probably helps if I reviewed these before.
there it is. So
Okay.
shifting.
So we have a clock down here on the bottom. And on this rising clock, okay, we're changing the first stage to a 1. And on the next clock, it goes to 0, and that 1 shifts to the next stage. So in the next clock, it shifts down 1 more, and then it shifts 1 more, and these can be as long as you can make them.
Then it comes back.
It can. It depends on what you're trying to do with it.
Your NOR gate there. Back.
The one place I was familiar with using these was doing encoding and decoding for radio control models. So you have a pulse train that's pulse width modulation, and they're in series. So you would use the shift register to determine which channel was which as you shifted it through. You get each channel because they're all in. It was real simple to implement. Takes 2 chips. As far as the exam, you kind of need to know what a shift register does. It shifts bits through. Okay.
So PWM obviously is pulse with modulation.
Yeah, this chart is pulse width modulation.
Yeah.
There are chips that do it. In this case, the simulator I'm using has one. And basically, it will take an analog input and give you a varying width square wave out, or we call a pulse width modulated signal. That's the width of the pulses are proportional to the amplitude of the input signal. So in this case, if assuming this was balanced, so when it's 0, we're going to be at whatever the mid range would be. So when the voltage is higher, the pulse widths are going to increase. And then as it goes negative, they're going to go to minimum. And it's very easy to decode this or demodulate it. All you need is a low pass filter or an integrator.
Your clock rate has to be certain speed above, like 3 times at least,
For what?
to decode it.
Oh,
Like,
yes. I can't think of, they maybe do. Any idea where you use PWM in a amateur
I don't
transmitter or
know,
receiver?
never using it. Cell phones used to use it.
Yeah.
I don't know if they still do or not.
I don't think PWM's on the exam. It's just there so you've seen it. I believe there's a question about comparators. And what a comparator does, it takes an analog input, compares it to a reference value, and will generate an output depending on whether it's above or below that reference. So in this simulation, we've got a 4-volt reference signal coming in, and then the sine wave, which is looks like 0 to 8 volts. So whenever that sine wave gets above 4 volts, which is where we're starting, the output of this comparator is going to be true or high, probably 5 volts, depends on the comparator. And it will stay in that state until the input signal goes below the reference voltage. So you can see in this sine wave coming in, we're basically generating a square wave.
I mean, as soon as it drops below 4 volts, and the output will drop to 0.
Right.
Okay.
Now, in the real world, these will also have what we call hysteresis. And it will be set up such that when this signal gets above the 4-volt reference, it will switch, but it won't drop until it gets some amount below the 4-volt reference so that noise doesn't cause it to toggle all the time. If you had a 4-volt signal coming in here and just a little bit of noise on it, all you would see is back and forth, square wave noise pulses coming out of it. So when you add the hysteresis, depending on how much it is, if it's well, let's say for an example, it was 1 volt. So this wouldn't go back to 0 until the input got below 3 volts. So you'd have 1 volt of noise immunity.
It would switch high until it got to 5 volts.
Yeah, if you do the hysteresis balanced.
Yeah.
There may be a question about hysteresis.
Huh?
So I'm thinking, on one of the exams, there's a question about hysteresis on these.
I don't remember.
I don't remember either. But that's for week after next.
Now, yeah, that was just a quick question. The end of this particular course, what is the how many more weeks? I didn't have that on my calendar.
Oh, well, the technician class starts on the 27th. And that's where we actually go over all of the exam questions.
Gotcha. Okay.
This is just trying to give you an overview of a lot of stuff.
Right, but the technicians runs from 27th through what?
7 weeks.
7 weeks. Okay.
And there's 10 sub-elements. And I'm trying to spread those out over those 7 weeks. And within those 10 sub-elements, there's 35 groups. So there's 35 questions on the exam. You get 1 question from each group. And a group is typically 10 to 12 questions. So it's kind of random. You have no idea which group of 35 you're going to get. And in fact, there's 12 exam booklets. So there's 12 versions of 35 questions. And we go over every question. There's 410, I believe it is. So we'll go over every question and what the right answer is and point out why some of them are wrong. Some things to help you remember what the right answer is. In a lot of cases, it's just a matter of carefully reading the question. And there'll be one.
Oh yeah,
or
you
two.
can easily Yeah, you can easily rule out two just by
Right.
educate. Yeah, just two you rule
Normally you
out,
can eliminate
and
two
the
real
other.
easy. And then
Yep.
on the other one, there may be one word in the question which will really tell you which of the
Yep.
other two it is.
Yep. Exactly. Hey,
Okay.
just real quick, not to take you down a rabbit hole.
No
The
problem.
download the download manual that you sent out. Did that have
Yeah.
any practice exams on it?
No,
Okay.
you need to go online. You can go to the ARRL site, arrl.org,
Yeah.
and you can do their technician practice tests for free. You don't have to be a member.
Right.
There's hamstudy.org, which a lot of people like. And there's a bunch more. If you just search online for
Yeah.
technician practice exams, I mean, there's probably a dozen.
Yep.
And you will need to do the practice. You need to get up above 80%. I would say 85%, and you're good.
Sure.
If you're consistent around that, because you have to have 74% to pass,
Mm-hmm.
which means you can miss 9. But for me, the hardest ones on the technician exam are the rules and regulations.
Okay.
That's where I had pretty problems.
It depends on, I mean, the technical stuff was easy. Rules and regulations, you just got to remember it. It's just memorization.
Yeah, because it becomes a word game. They start throwing in words and phrases that either do or do not match what's in the regulations, and you just got to be you got to read really slow.
Yeah. And I think I sent you a copy of the FCC Part 97.
I'll take a look and let you know.
Okay, if not, let me know. That's where all the rules and regulation questions come from. But it's not the easiest thing to read because it was written by FCC lawyers.
And you said that was FCC Part 97?
Yeah.
Okay.
But it does maybe give you a little more explanation on some of those rules and regulations. Okay. Analog to digital and back again. We can go both ways. You will see analog to digital converters in your modern radios, particularly if they're SDR or software defined type radios, where we take an analog signal in and convert it to a digital output in the range of 12 to, I don't know, they might even be up close to 30, 32 bits, definitely in the 20 range. And then taking that binary representation of that analog sample, because we're going to sample this at a very high frequency, you can do software manipulations and implement filters and all sorts of things in software or firmware. You can actually make filters that you can't build in the real world. I mean, you can make almost like a brick wall filter where the skirts are essentially vertical. All kinds of transforms and easy to do single sideband using the Hilbert transform, which is on the extra exam. Then we can go the other way with a digital to analog converter, which takes a digital binary representation of X number of bits and converts that to an analog signal. And there's a couple different types. There's a flash converter, and remember what the other one is for D to A? No, I can't think of it. But essentially, it kind of does an envelope detection on that digital signal. It'll have a low pass filter on the output of it and give you an analog representation. Like in the case here, if we start off with this analog signal, we fed it into the sample and hold, the analog to digital converter. We did some stuff with it, like filtering. Eventually, it goes back to a digital analog converter and a final filter, and we'll get the output, which, depending on what we did with it, will look like the input, or it could even look better than the input. If you're doing this as in audio, there's a lot of processing that you can do to improve that audio signal. So this input could have a lot of noise, some distortion on it, and in software, you might be able to eliminate all or most of that. Okay. Any questions on those?
We've lost it.
Nope.
Oh,
Well, let's see. If I can. See, what do we have to 10? Oh. Now, this is stuff.
record.
First, I have to stop.